Kind of good. Okay. All right, guys. We'll get started. If you remember from the class curriculum, I was going to switch from one module to the other, but it turns out you guys ask enough questions that I will essentially make that all very smoothly. So we will be talking more about mechanical properties. We will be talking more about corrosion as we get towards the end of the 12 hours, but it's not like today I'm going to stop talking to you about heat treatment. I think there's still things you guys seem to be very interacting and learning stuff. So I decided to expand a little bit the situation we do with surface treatment of fasteners. There were a lot of questions about bolts versus welding. So we'll get into more details of that. And the surface treatment really ties into all these phase transformations. So I think this is actually going to go very smoothly. And in the end, you know, as a processing overview, when we talk about corrosion, I'm going to talk about ways to prevent corrosion, which has really been this past maybe 40, 50 years, the reason why we continue using steel. We do protect it, so it doesn't start staining and rusting for up to 30 years out by the ocean. And it's essentially new technology and new techniques, the same. We didn't reinvent the laws of physics, but we got much better at dealing with steel structures for new installations. And then going back to the Longfellow Bridge and other situations like this, it's always, you know, a difficulty. It's a big challenge to maintain existing structures that were designed differently, that didn't have a zinc protective coating and all those conditions that we now try to promote for each new project. So again, I think it's going to go gradually. And there were some questions yesterday, or follow-up questions you had about thinking about fracture toughness, strength, and grain size. I think my main comment, if I go back and try to see, like when I was trying to make these connections, the main idea is the deformation, the plastic deformation needs to happen in the grains. And why is that? So if I'm looking at multiple grains together and I have a bunch of triple zones, and so I'm going to be very idealistic here. And right now we're talking about conventional grains, so micro size. They each have their own orientation. So say one has a slip plane that likes to slide this way, this one has it this way, this one has it this way. When they all move, you have a high energy boundary here, all these grain boundaries. These actually won't be places where you have the most deformation, because what needs to happen is you need to shear one of the grains in a certain way, shear the other another way. You try to accommodate what each individual grains wants to do. So when we're talking about cracking, first of all, cracking is generally caused by plastic deformation. So if I have a crack in the material, yesterday when you guys went through the concept of stress intensity, so say I have a sample, it's got a crack, that's a length, and I'm loading it here. So I have a defect length of say A here. It's pretty big. Generally, for steel, you need a big defect to really start having a fracture of the steel. What happens here is very, very, very different depending on the alloy or the material. If it's a very brittle material, you can just slide off and propagate right through the grains. And that's the cleavage fracture. It doesn't absorb energy. What is most common when we talk about grains, we're talking about metals, is you're going to have some plasticity. So you exceed, if you remember when I was talking about the stress strain curve, we had stress here and we had strain. We have the elastic behavior, then we start having the plastic behavior. At the tip of the crack here, unless it's a very brittle fracture, you're going to be yielding. So this material here is going to be deforming, and you know, not as much as in a forming operation, but almost. We're talking 30–40% strain. To accommodate the stress intensity, it's impossible for the metal to resist very, very, very high stressors, so it will stretch locally at the crack tip. Now, the way it's going to stretch here is by all that deformation in the individual grains, and if we're thinking about accumulating damage, which is what we're considering here, well, you're going to accumulate damage where your deformation is, and primarily your deformation is inside each grain, because these are kind of bonded interface. This is a place where if I'm sitting right here at the grain boundary, which slip system I'm going to choose? You know, I got one side one way, I got the other side the other way, so I can't move. And the deformation is primarily an activity inside each grain. Now, if you go to the nanograins, what happens is you're reducing the domain where all that activity is taking place, and that's why your strength is going up. Are we good with that? Grain size. So I'm looking at, say this is, I don't know, 1/1 row of whatever you decide to use for equivalent size. If you have less room for, you know, all these Frank Read source, if you remember, we have this going on, and then you start forming dislocations. You have one, and you start trying to form another one here. You need room to do that. So the more constrained you are in space, the more hardening you get and the more stress it takes to deform. There's really nothing, I can't simplify it more, unfortunately. What I could say is the only time where the grains will have an effect on the value of K here. So you have your fracture toughness, Kc. That's more or less a function of the stress level, and the crack length. This is K1. The material properties are different. So this is just the demand. This is what you apply. So if you have a material that is very, very low fracture toughness, it's going to start breaking when the stress intensity is fairly low, something of the order of 15 KSI square root of inch or something like that. If it's a very mild steel, you're looking at a number that's more towards 200. So with that respect, given that we have a square root factor here, if we have a range of 20, it's a range of 400 in the capacity to resist cracking. So it's a very, very large difference between a ceramic and a piece of metal. And therefore, we use fracture toughness. We actually use this concept for large cracks. The project I mentioned a little bit about the transmission towers that are coming down, they have cracks that are inches long. And that's a situation where it's big enough here that this stress is a kind of stress that they can get from wind loads, and therefore the crack continues to grow. And it continues to grow because you have that plasticity here, so wind comes in, you stretch the crack. Wind goes the other way, you reclose the crack, and as you do this, you're just opening it. Opening and closing, and you're moving forward. So you tear one time, you close, you tear again, you close. And that's why we have a lot of times these fatigue striations for each cycle of loading. And they all involve a lot of plasticity that relates to those grains here. So it's at, I guess, a deeper level that what I really wanted to do for the overview. These concepts are actually going through a lot of this in fracture and fatigue class, and that's 3.35. We offer it every other year, so we're going to do it in spring of 2016. And that's with Dr. Dow in Material Science Department. I do about a third of the class that I go through the applications and how you actually apply damage tolerance. So you deal with a crack that is existing and you study the progression of it. Yes?
So you talked about cracks being plastic and their deformation. So how is it opening and closing? Once it's open, it probably stays open, right?
It stays open if you're applying a constant load. But most of the time in an application, even a bridge, you're going to have cycled through the year. It's going to go from the heat of the summer to the cold of the winter. So those are cycles that you can see after the fact on the fracture surface. So if you have a crack, it's very rare to be in a very constant load situation. So it's normally if you have a crack, unless it's coming from processing and your loading conditions are very, very low, generally it will grow. And it's acceptable for power plants, for aircraft, for car components, boat engines. It's just a matter of how fast you're willing to have it grow, and and what's the useful life. So it's a little. It's how you optimize. It's how you save money by making it able to resist cracking for a certain time, and when you start to crack, it's going to grow hopefully slow enough that you still reach your useful life. Or you inspect and replace. So it would be very hard to make an aircraft that will not crack in service. It's easy enough to make large structures like bridges. You really hope for bridges to not have big cracks. But they do sometimes, and because these structures are so big, you hope that even by visual inspection, you can identify those cracks. And when you find them, then you have to determine if you're going to do something about it. If it's a 1/4 inch long crack, you don't need to shut down the tunnel, most likely, unless it's a very, very high strength steel. A very, very high strength steel is going to have a much lower fracture toughness, and they have to worry more about it. It's a very good question. Anything else? All right, let's go with today. We're back to the Martin site. And the reason I want to talk about Martin site again is there is one situation where we almost use it as is. We don't go through the tempering to reduce the strain. And these are self-drilling fasteners. So I'm going to pass those around. I've had, I think, a dozen projects where people came and they were very unhappy because on the building, and the worst was a place out in Alaska that they were putting at this big warehouse for processing something. I forgot what it was. And building's only a year old, and the big panel that's supposed to, be the enclosure started flying all over the place on their campus and hitting other structures, and they were not happy. What happened is, of course, it's very cold weather, and they had panels that were relatively thick that had built-in insulation. So you just put up a frame, you come with these thick panels, and you build it up. Now, the fastener they were using were similar to these, where the bit, the tip of the fastener has a bit end. So it will drill the hole exact wherever you drive it, and then attach to it. So you see here the threads were damaged, so it went all the way to here. And then you even have a seal here, so it's all very nice. It's a very quick operation to do everything. As I said, it didn't work, and there were a number of reasons for that. The first one, they didn't put enough of these, and there was also a defect in the fastener itself. So I'm going to show two cross sections. You can see the bit on one. The other one is actually another fasteners, but the main point here is what we're going to look at on some of the cross section is etch. That's how you can see the different phases. You just put an acid, and it's going to dissolve preferentially one phase as opposed to the other, and that's why we see all these colors. If you just polish it, it looks like this, but when you etch it, it's when it becomes darker. And it's not perfectly clear because this being old at this point, but it is darker on the surface all around this one. And that's the carburation treatment that we're going to talk about today. So you can pass those around. This one, it's an example of a fracture. Is this fracture field? Yeah, this is a field fracture, but there was something wrong with it. So that failed in bending. And this, kind of a combination of bending and torsion. The smaller one is from my house. And it's the fasteners to hold the gutters. So you have this clip inside the gutter that people don't see, so it's all nice and cool. And then you connect to the frame of the house. So it's all concealed. The gutter pattern is right over here. And it's really not a question of strength of material. In fact, this is all bent right now. I don't remember what I was doing, but I replaced high strength steel fasteners with just low strength stainless steel ones, and now I'm fine. I don't think the diameter is significantly bigger, so it became brittle. And it happens with those high strength fasteners, and we'll try to go a little bit into that because I'm sure you're curious about it, and I would be too. Yes?
Is this supposed to be a part of this?
Is it the exact end? It's really the same job, but it could be too long. It could be that these are separate. One is cut.
Yeah, one
It's
is
just
cut
to
and
show
this
the
is
end. The
flat.
other is the fracture. Yeah, so I don't think they match.
Okay.
Yeah. We had very few heads, just the way because the panels were going and the heads were going away, so we've never been able to match one piece to the other, really. It's nice to have a matching set, just doesn't happen. Okay, so just to go back to that martensite, I said we have the high temperature austenite. Those are the black. Forget about the brown. It's a very compact. Each face of the cube has an atom in it. And that makes you got 12 ways to have sliding in that structure. It's really cool. Now, if you cool it down quickly, you don't have diffusion. You're going to that tetragonal phase where it's stretched in one direction. You get a 4% increase in volume. And we call it a military transformation. It's a little bit like twinning. So everything shifts by a certain amount inside a grain. And that's why we see these little needles. These are essentially slightly different orientation of the crystal because you needed to grow, and to grow multiple grains, they need to deform differently. So you have needles that are very different orientation in each grain. And that's because you want the whole material to hold itself. There's a lot of energy. If you wanted to create mini cracks here, there'd be so much energy in trying to separate the metal that it doesn't happen. It just stays with less deformation. Each grain, this one's going to go this way, this one's going to go this way, and they all stay together. Very little deformation at the grain boundary itself. Now, the way we get there, if you remember, is we have to avoid forming the equilibrium faces. So if normally we will get that perlite, that's the upper green half circle. To get the perlite, you just cool off slowly and it will form. And we talked about last time, Wednesday, on getting it finer or coarser depending on your cooling rate. But to get to the martensite is all the orange stuff here. You have to go very quickly. And on this diagram, for example, we see that we're likely to get the bainite, so this lower green region, or some bainite on top of the martensite. And that's all dependent on the composition, and it's dependent on the cooling rate. I did promise you that I was going to show you another way to think about quenching, and it's this one. Here, when you see those lines, the orange line, it's associated with a certain cooling rate. So you have 7 degrees per second, and then you have 0.3 degrees per second. You're starting to cool much more slowly. 0.06 degrees per second. So this is more or less if you let it cool in the oven or in air. So it tells you how fast you need to cool at the area you're trying to transform to not have any austenite transforming into bainite to go all the way to the martensite. So call these continuous cooling diagrams. They're really useful if you know your alloy and you can get an estimate of your cooling rate. You can use that to determine, oh, am I going to need to quench in oil, water? Can I do it in air? That will be determined by these types of diagram. Certain stainless steels will form the martensite just by air cooling. And because stainless steel's got chrome, nickel, it's got a bunch of alloying element that will really postpone the regular transformation, and therefore you don't need to quench them and you still have martensite. It's not necessarily what you want. Sometimes you want a combination of martensite and another structure for getting more ductility, but it is one way to do it. So I just wanted to wrap up before we get in the details of those fasteners and the surface treatment. That if you remember, we started with the phase diagram. We looked at what will normally form. There's an eutectic reaction when we were in solidification, or in the case of steel, we have the eutectoid reaction. So we went through the details of that. When we were in aluminum, I said it was very different than the case of the steel. So aluminum was I have a lot of solubility at high temperature. So I'm here, I got a single phase. I put everything in solution, I quench it, and I go back over time in temperature and heat it. And that's where I have the aging. It's for aluminum alloys. It's used for certain types of stainless steel when you're looking for good ductility and strength at low temperature. With the steel, we went through that a number of times now. The main difference is we're going to the austenite. So at high temperature, we have the austenite. That's our stable phase. And everything happens there where you cool it off, and then you either go to the equilibrium reaction. So we have we're either forming the pearlite or the bainite. So that's alpha and Fe3C. That's the cementite here. Or if we go really quickly, we form the martensite. And then we go to heat it up again, and that is our tempering. And if you could remember, in aging, you get stiffer. So that's the aluminum. When you are tempering, you just smooth it up a little bit, because you were really, really hard after that quench. When this went down for the quenching, you had to come very hard because you had you had a phase transformation. The reason here you don't go hard is you don't do anything. There's no phase transformation. Yes?
When you temper the martensite, you're increasing the temperature, right?
Yes.
So shouldn't that be unstable because it was formed by shock cooling? So
Yes. So it wants to automatically transform back into the equilibrium phases.
oh,
That's perfectly true. So because it's that quadratic cube structure, it wants to go back to iron and cementite. And the same way that the aging of aluminum, what happens is the temperature you go at is going to determine how fine that microstructure is going to be. So, and because steel is such a high melting point, there's really nothing going on until you actually heat it up. So there won't really be much natural aging with steel, which we said we had with aluminum. Good. Yes? You did, I'm sorry.
What?
You had a question?
Oh, no,
All right, the surface treatment. I'll show you why we do it. If you want to make a piece of steel for wear application or for cyclic loading application, you want that steel to be resistant to fatigue. What you'd like to do is have the surface pretty hard. So high hardness reduce your wear rate. It's almost universal. Unless you have really some brittleness that comes in and all of a sudden things change. But otherwise, it's really good. Having strain hardening, like I mentioned, we use precipitation hardening. So aging type behavior for stainless steel bearings is the same way where if I start to deform it, if I have trying to make a scratch, it will become stronger at that location and resist the wear pattern essentially. So you try to get your surface hards, and I think you'll agree with me that it's one thing to crack the surface in service. So if I have these fasteners and the first 100 micrometer cracks when I drill through and do my installation, it doesn't mean failure. It's all about whether that crack is going to grow or not, and whether it grows or not depends on the property in the core. So that's why for a lot of application, there is an advantage as a function of depth. So this is the depth underneath the surface to have the inside high toughness. And high toughness correlates with lower strength. And you want your surface to be super high hardness, so you try to minimize forming cracks, and you try to maximize your wear resistance, or both. So that's why these treatments are done. In the case of the fastener I'm passing out, the drill bit, you want the drill bit to be much more resistant than the other piece of steel it's going to go through. And it's okay if, every once in a while, break it. They'll drill another hole next to it and get away with it. And it's not really for long-term use. And that's why they treat those surfaces. They take the same steel, and you essentially have carbon that's going to penetrate the surface, and then you go through the heat treatment. So here's the sequence of the carburization process. You go back to the high temperature austenite. So this is, I'll say greater than 700 degrees centigrade. So your little fastener, it's all formed, by the way. So that's a nice thing. You can form it. You can cut the threads. You can do whatever you want. You're ready. You put it in the oven at high temperature in the austenite, which is this structure. So at high temperature, there's plenty of room for carbon in this structure. And you try to get close to the eutectoid concentration, if not even a little more. So you put quite a bit of carbon into your microstructure. If you remember, this location here was 0.8% weight percent carbon. And you put somewhere between 0.8 and 1% typically on the surface. And you do this relatively rapidly because it's not a super long or expensive process. You heat it up. You have a gas containing a lot of carbon, and you cool it down quickly. And by cooling down quickly, we go through the same process here of forming the martensite. So now we have martensite on the surface, and it's a high carbon martensite. So martensite has different hardness depending on the carbon content. The more carbon you have, the more hard the martensite is. So going to those threads, I'm gonna just show you the microstructure right away. This is what you see on the surface. It's really dark. It's hard sometimes. This is somebody who was learning polishing, so it's not the best polishing job, but it's something that needed to be done very quickly. We needed to know what was going on. You're looking at this layer here. It's about 200 micrometers, and you can see the very fine, darker microstructure. So this was carburized, and I didn't know it until we cut and polished it. It's not information that's necessarily available to the end user. When you go to the core, it's a fairly different microstructure. This was quench and tempered. So they went through this series of processes essentially to make this microstructure. So this one was also tempered. It wasn't a 65 hardness on the surface. It was less than that. Where we had 65 was on the tip itself, the part that you see in the self-drilling part. So they had to come and do a preferential aging of just the structural component of it. So we can think of it as being, pretty sophisticated process, but the bottom line story with a fastener is the bigger the fastener is, the bigger the hole. So the harder it is to get it in there. No matter what you do, like if it's a guy that's on a scaffolding trying to put these fasteners in, he would rather not have to have like a press drill to try to get his stuff in there. Sometimes they end up doing it. We have portable press drill, but if you can avoid it on the final siding, it's very typical with especially screws in wood to try to get the smallest diameter you possibly can. Yes?
Wouldn't higher carbon content of the martensite make it more brittle?
Yes, it does. And that's kind of what we're looking for the bit. It's brittle, but if you're thinking about drilling, it means one material is going to act as if it was diamond or carbides. You don't want it to deform at all. So you're looking for a difference in the hardness that's something of the order of 50% harder. So it remains elastic in that process. And you're not also loading in tension. It's more or less of a torsion and shear application. But it's designed to the limit, and that's why sometimes it breaks. If it breaks during installation, normally people know about it, and it's not a big deal. What you want to try to avoid is the failure over time. When it fails over time, this is going a little bit towards something I'm going to talk about next time. It has to do with the corrosion protection. So what we're looking at here, the image is not perfect, but just a piece of sheet metal. So this is the backing to any kind of application. So you have, say, the final building panels that are getting screwed with the fastener through this plate. That's all it's held. And these plates are held to the main building frame. So it's just an intermediate step here. And what happens, I mentioned about galvanizing, you can see here on the cross section, this is not matte. We don't see what's going on in the steel. This is relatively low strength steel. But you see the little galvanizing layer. It's very common to have a galvanizing layer because you have moisture. Even if it's not exactly exposed to the rain, there's always moisture in the walls, and you don't want them to corrode over time. So you put that galvanizing, and what it means down the road is you're going to be consuming zinc to protect your structure. And the main consequence of that for these types of fasteners is depending on the acidity, you can form hydrogen during the service. And that's where a lot of these fractures occur, because the hydrogen makes the grain boundary weak. If we were talking earlier about this, I said, we got all the deformation taking place here. That's great, no problem. But if I have sacrificial protection of zinc that somehow creates hydrogen, the hydrogen will be preferentially at the grain boundary. It fits in there, and it's reducing the energy of completely separating that boundary. You can think of it, if I put enough hydrogen, it's going to want to form a bubble of gas, right? So to separate between the two grains, especially under high load. So now you're going into a very different process. We went through all this difficulty of forming the martensite. We're preventing here deformation in the grain. And if in service we have the generation of hydrogen, sometimes it's in processing also. If you do an electrochemical deposit of the nickel over a coating, you can get hydrogen in your microstructure. So this becomes stronger, this becomes weaker, And then all of a sudden you can have that very low fracture toughness because you'll just unzip through the grain boundaries. And I have plenty of images of that. It's something that's nice because you see the grains. If you want to know your grain size, you can just expose the high-strength steel to hydrogen and break it. It breaks at very low load if you have high hydrogen. I think what I want you to keep in mind is all of this is typically there. There's always a little bit of hydrogen, and there's always dislocation in the grains. And the question is, when are you reaching the critical point where you're going to go from one process to the other to create the fracture and all of a sudden lose, say, a factor of 10 or in fracture toughness? And well, that's where you need a little bit more details, essentially. You need to know, well, what's my concentration of hydrogen? What's the yield strength of the steel here? For structural steel, I'll throw just a general number because there is a big range. Well, so I'll say 32 to 40, depending on the environment. Rockwell C is when you start changing from the deformation inside the grains to propagating through the grain boundaries if you have hydrogen. And that is why a lot of the heat treatment for fasteners target somewhere in here. Some I've seen before, some manufacturer target 40, and those are some of the things that are circulating around. They did fail in the brittle matter. So closer to the lower end is what you would normally want to do. I've seen in the oil and gas industry maximum hardness of the order of 32, sometime up to 35 Rockwell C, just for that reason, for trying to make sure it's going to deform here as opposed to have the decohesion on the grain boundary because of small elements like hydrogen segregating in there. Yes?
When you're carburizing, how do you actually heat it up and get the carbon in?
You can just circulate a carbon dioxide or carbon monoxide gas through the furnace. But you have to heat it up of the order of 800 degrees so you are in the austenite stage. It's not super expensive, and the duration affects how deep your carburation layer is. It's really neat because you get this gradation essentially. On the surface going to be the higher concentration, and then you go less. Yes?
Is this the thing that happened to the big bridge?
Which big bridge?
There was hydrogen embrittlement of the bolts.
Oh, I don't know about that one. But if they said hydrogen embrittlement, it will be related to this, yes, for steel. That's kind of just it. It's interesting because it ties into the grain. It mixes everything together. Yes. Yes.
Is carburization self-limiting in the sense that if you saturate like the top layer with carbon so much that it'll prevent more from diffusing it? Or could you keep it in there forever and it's going to all completely embrittle itself?
It's a good question. I think normally you put your gas concentration in the furnace so you reach an equilibrium on the surface of the order of 1 or 2%. It's the carbon activity, if you will, in the gas. So you avoid forming, cast iron phase on the surface. So that's how you try not to go too high on the surface by using equilibrium of the gas with the top surface. And I didn't talk too much, but you can do the same thing with nitrogen. Nitrogen is also a good way to increase the surface hardness. It's a small element. It does the same thing. It gets into your microstructure. The carbon in the microstructure in solid phase really just prevents all the dislocations from moving, essentially. So, yes?
If you do have hydrogen segregating your grain, is there a way to get it out?
Yes. So if it's coming from manufacturing, you heat it up and it will go away. It's when you do electroplating, it's one of the important part of electroplating. If it's coming from service, from that galvanizing just getting consumed, you're out of luck because you're going to continue forming it as you go through the service. And that's one reason why the very high strength fasteners they don't sell them galvanized because you have that risk. If it's a little acidic water, then they're all going to crack very quickly. It's a big problem. Same for very high strength steel used in concrete, in pre-stressed concrete cylinder. They have to stay away from chlorides and hydrogen because otherwise they'll crack. Yes?
So how do they then have the corrosion protection if they can't use like,
It's a good question. So the main way for high strength material that I'm familiar with is you embed them in grout, and that keep a passive layer on the surface because you're in a pH of the range of 12 on the surface, and then those conditions, the steel, a little bit like the aluminum at ambient temperature, it's got a passive state on the surface. And that's the main reason why we do put steel in concrete. Now I'll say we galvanize more and more steel that goes into just regular concrete, but this is structural steel. It's not very high strength. So the high strength stuff is when you have these big beams for the overpass, a lot of times what it is if I'm looking at a section of it, it's a big concrete section, and then it has strands. So over here you're going to have essentially metal ropes that are loaded in tension. So you cast everything, and then you pull. As you cast, you pull on the steel to very, very high stress levels. That's why we call it pre-stress. When it's all cured, when the cement or concrete is all cured, you let it go. And you keep that steel in very, very high tension. But a lot of times they'll put a special grout around these strands. Or they even, you can have, depending on the system, you really try to prevent the environment from getting there and start breaking your condition. Otherwise, you have parking garage repairs all the time when it wasn't done correctly. You save money. You use a small amount of steel and a large amount of concrete. You isolate it, but then when something goes wrong, I've had projects when I worked for the big structural engineering firm where the cement company had impurities that they didn't realize they had, and therefore the whole system was affected by it. It's very, when you're relying on a protection like this, it's difficult. It's difficult to ensure, a certain reliability for all conditions. You just need a little crack in the cement or a little impurity, and then all of a sudden you start corroding or cracking. Cracking is the worst. If you have some chlorides, I've seen these strands. They can be as big as say a 1/4 inch in diameter and just pop right off. And it's almost, you could use it for cutting. It's almost like a knife because it was brittle. Yes?
Can you do something by adding a potential to these connectors to prevent that from happening?
Yes. So about using sacrificial protection to prevent the corrosion. You have to keep your voltage below a certain amount because otherwise the sacrificial protection forms hydrogen. So it's just a practical limitation. If you don't protect enough, you get general corrosion. If you overprotect, you get hydrogen cracking. So there's a very, very narrow window of potential for protection that works. Now, if I have a pipeline in the ground, I have all the soil, what I can do is I can put my sacrificial system or my corrosion protection system, I got plenty of room to put it. If this is a beam in a parking garage, the problem is where do I put my 2 electrodes for sacrificial protection? So that's why in practice it's very expensive, because if this is only going to have so much moisture in the concrete, what they find is you almost have to put a sacrificial anode every 3 or 4 feet. So it's becoming a very complex system if you have a 64 feet beam to have all these cells that act for the corrosion protection. It is done in parking lots sometime when they have a repair locally, because they're already opening everything up, and they'll run some electrical system essentially to feed these sacrificial animals. Bless you. But if I'm thinking about a new installation, well, it wasn't done yet as of 3 years ago. We were proposing it for some existing installation as a retrofit, but there were a lot of people not necessarily wanting to do it. You start creating, you have to get close to these metal wires if you're going to protect them. If normally you have, say, a plastic conduit here, which they do sometimes to isolate the steel from the concrete, it means you have to go back and perforate through that layer to create your protection by current. So pipeline, it's great, and we will talk about it in more details. I'm realizing that I'm just throwing some words here, sacrificial, why don't impress current, all that. We'll get to that because it's used a lot for pipelines. If I have a big pipeline that's a high strength steel, but not too high strength that it will break when I have a little hydrogen. That's kind of what I'm thinking if I'm building a pipeline. And I want to weld it too. So there are a lot of reasons for not having it too hard. The great thing about the sacrificial protection that we're going to cover is you still paint it. You still put a protective coating on it, because otherwise you'll consume way too much current just trying to prevent the corrosion. So you coat it, but any little defects in your coating is where you just consume electricity essentially to compensate for and prevent any local loss in section. Yes?
You could also have more passive sacrificial coating, right? Or sacrificial protection, like on a ship where you just have another metal on there, which basically oxidizes the other one and prevents it from rusting.
Yes, and that is very easy if you're in water. Because in water, so if I have a ship, and they do it even with aluminum, like performance aluminum boat, if you put it at the dock for a couple of weeks, what you do is you drop some magnesium around the boat. It's high performance, so you don't put them all the time. And then it will react and protect the other one just because you make the electrical connection metal to metal, and then the water acts as the fluid. It works great for pumps if they're not running. If the pump is running, then you lose the ionic transfer here. The flow, it just goes with the flow, so that type of protection doesn't work. On the same way with pumps, if pumps that are running are not really too much likely to, if I have two metals next to each other, to have that interaction and galvanic corrosion increase in the corrosion rate, because they're not effectively sharing the same water, the same electrolyte. But when you stop, that's where it can get stuck, because then all of a sudden there's a path, an exchange of ion corroding one as opposed to the other. So the plan is, one of the next steps is go through just a brief overview of welding. We've talked about it a little bit here and there, but I'll give you more background, show you a little bit the equipment and what it means. And then, corrosion is something I realized over the past couple of years you guys are interested in, and I happen to have experience. I'm not a chemist, but I've dealt with it quite a bit, so we'll spend some more lectures on that. Thank you.